Well, Dave and Jeff, thank you very much for getting this set up and for also helping us set up the recording here this morning. Also, I'd like to thank everyone who is in attendance today. The objective today is to talk about the geostationary lightning mapper. And I have a couple of things I want to discuss in this outline today. The first thing is I want to do a very quick overview of the GLM operational assessment. That's what has kind of driven creating this particular webinar. It was designed as a kind of a pre-assessment webinar for individuals to hear a little bit more about the geostationary lightning mapper as that's soon to be in operations, and to have the opportunity to ask questions about the geostationary lightning mapper ahead of the assessment. In addition to that, in discussion with the various regional headquarters, we decided that we wanted to make sure that this information was available to everyone, not just the offices that were participating in the assessment. So that's why we're doing this here today, also doing the recording here today. In addition to showing that very brief outline of the assessment, we'll be talking about the GLM instrument itself. Again, kind of a brief few minutes, talk about the instrument, what it is, how does it work, and the background of the type of observations that the GLM provides. I'll then drop into a couple of operational uses. Now, these are using some demonstration data prior to the beta release of the GLM. So again, designed for kind of some early food for thought type examples, how we can use the GLM operationally. They're kind of designed to be shown to be very short and to kind of, again, foster discussion back and forth of what are we looking at and how can we use this in operations. Lastly, as the GLM is now in its beta status here as August 3rd, I do have some sample GLM imagery so that we can demonstrate that, show what you're looking at, and how it may look in AWIPS going forward. And please, at any point, if you have any questions about what we're discussing here today, please feel free to ask any questions throughout the presentation. And also, I have some kind of natural breakpoints as we transition from topic to topic to kind of open it up to discussion. So the first thing I want to talk about real fast is the GLM operational assessment overview. This is kind of an activity that I'm performing as part of my role as the geostationary lightning mapper satellite liaison. And kind of following the NASA support paradigm of where we're trying to identify forecast problems, kind of match that to forecast operational needs, and really kind of understand how can we use the GLM in operations. This assessment works in very much a complementary role to the hazardous weather testbed. Hazardous weather testbed had the opportunity to bring forecasters from around the country into Norman, Oklahoma to look at some of the test data but prior to it going out to the field. We're complementing those efforts by taking the lessons learned from the hazardous weather testbed and now bringing that out to doing the assessment at your local individual offices and CWSUs. This gives us an opportunity to really test out how does the GLM work on a day-to-day basis with all the needs and concerns that are going on inside an operational office. So again, we're looking at a real-world setting, but we're also trying to make sure we minimize the impact on your time. We understand that working in the operational environment, you're on shifts, you have multiple things you have to be doing. So what we're attempting to do is we want to have a short Google document survey at the end of the day that you can fill out at the end of your shift. We also understand if you're possibly working on a severe weather day, you may not be doing that at the end of your shift. You may fill this form out later on the next day or the following day that you're back on shift. We understand that, and that's exactly how we want to be able to work with you on this. We don't want this to be very intrusive. You have the opportunity, we just ask that you put your office, so at least we know the geographical location of where the assessment came from. But if you do feel like putting your name on that particular form, we'd love to hear it from you, and that way we have the opportunity to kind of follow up on kind of any more in-depth questions that we may have about the case that you are submitting. Now, what's going to happen with all this information that we gather about the GLM and how it works in your operations? What we really want to do is we want to take the opportunity of the cases and the examples that you show and develop further examples for training and an applications library. So this is an idea of where we're taking examples that come from the field so that we can use it more as a peer-to-peer training process to other forecasters out in the field. At the same time, too, we're making sure that the feedback is going to the National Weather Service and NOAA development for the geostationary lightning mapper. So this is an opportunity for you to have an influence on how are we going to be using the GLM going forward in the years to come. Now, kind of dropping into the presentation itself, my name is Dr. Geoffrey Stano. I'm working with the NASA Support Program here in Huntsville, Alabama, but I'm also now serving in the past year and a half as the satellite liaison for the geostationary lightning mapper. So a lot of my role is work like this, outreach to the community to talk about the geostationary lightning mapper and look for the best ways to help implement this in operations. That's gone through training, working through the assessment, doing webinars such as this today. At the same time, too, I have to thank Brian Carcione from the Huntsville Forecast Office. He is the SUSE there. He's been very instrumental in helping throughout this whole process of kind of providing a operational perspective on the work that we are doing. So without his help and input, it would be very difficult to get to where we are today. At the same time, too, I would mention that the presentation that we're doing today is very similar to what was shown for the SUSE at the SU Prep course out in Kansas City this past winter. So kind of very similar to what we've done here, with showing some examples moving forward. So let me just jump right into it finally now and start talking about some of the details about the geostationary lightning mapper. One of the first things that I want to discuss is the concept of total lightning. The geostationary lightning mapper has the capability of observing what we call total lightning, and that's the observation of both intercloud and cloud-to-ground lightning observations. Generally, the intercloud lightning will typically far outnumber the cloud-to-ground in any given storm. So that's why we really want to be able to see that total lightning or the intercloud component of lightning. The example you see here on the right shows 31 thunderstorms. These came from Central Florida. Basically, warm season, run-of-the-mill type thunderstorms. None of these were severe. The red bars just indicate the number of cloud-to-ground strikes that occurred with each one of these thunderstorms. However, when we look at these 31 thunderstorms and apply the intercloud observations, we see a very different picture of the amount of lightning activity that was going on in each one of those thunderstorms. One in particular, kind of an extreme outlier, is Storm 23. That storm had no cloud-to-ground observations whatsoever, but it turned out to be the most electrically active storm of the entire bunch. As I said, that's kind of an outlier, but it does demonstrate the importance of being able to observe and see these intercloud flashes. By being able to observe total lightning, we do have several capabilities in the operational environment. So, those capabilities come about due to a physical reasoning of what is driving total lightning. The total lightning is being driven by the strength and volume of the updraft in the mixed phase region. Really, you want to start getting above the minus 10 degrees Celsius isotherm to really start getting to that mixed phase region. You really want to even get beyond that to try to get to minus 20 degrees Celsius. What you're trying to do, you want to get into a region where you have supercooled water droplets, ice crystals, grapple, all these various kind of particles bounced together to kind of create charge. The issue is, if you have a stronger, deeper, and more voluminous updraft, you're going to have much more lightning being generated in a given thunderstorm. So in a way, watching the intensity of the lightning or the total lightning in a given thunderstorm gives us an idea of what's happening to the updraft and updraft strength in a given thunderstorm. So if we see an increase, that tells us that updraft is strengthening. That's kind of increasing its intensity. An extreme example is a lightning jump, where you have a very rapid increase in lightning activity in a short period of time, and we can use that as an indicator for potential severe weather. Kind of looking at this graphically, the upper left-hand side is an image of total lightning observations, and you see a couple of features. One, you see this strong bullseye feature. This is indicating where the majority of your lightning is occurring. That's going to be correlated with your updraft location. We see that when you look at the corresponding image on the lower left, which is looking at the radar reflectivity at the 3.4 degree radar tilt. This is corresponding to the radar, not the radar, but this is corresponding to the mixed phase region on this particular day. And you see a very good correlation between that updraft location and the total lightning location. At the same time, too, we do see spatial extent. This is a feature that's brand new to the geostationary lightning mapper that has not been available either to the NLDN or the Earth Networks data. So in addition to looking for rapid increases in lightning to monitor convection and potentially use for decision support for severe weather, we can use this spatial extent information to get a lead time on the first for the first cloud-to-ground flash and seeing how far away lightning is extending away from the main core of the storm. For our CWSU partners, they may use this as monitoring convective activity. Is the convection strengthening, maintaining strength, or is it weakening? Is that going to have an impact on their TRACON gate locations, and will they have to reroute traffic because of that? Now, what we're trying to look at here at this point is this animation that I'm showing shows a single lightning flash that lasted for about 1.2 seconds. This comes from a high-resolution, ground-based lightning mapping array. As you see through here, as that lightning flash goes on, these gray lines through here, these are not roads. These are actually county boundary outlines. So this lightning flash is extending many tens of miles in every direction. So initiated here at this black X, and we see extending many miles in multiple directions. At the same time, too, we see the NLDN observations that were actually linked to this single flash that was observed by the lightning mapping array. So this is demonstrating that you can see that a single flash can actually come to ground multiple times. Now, this is one of the features that we have to understand about the GLM. The GLM can see total lightning, but it will not distinguish between intercloud and cloud-to-ground flashes. So that's one of the reasons why we need kind of the combination of both data sets. Now, what the GLM is going to attempt to do is going to take the information that we can see with this high-resolution research network and provide it over a much larger field of view, but of course at a lower resolution. So, what is the geostationary lightning mapper itself? It's actually not the first space-based lightning detector. Previous detectors were designed to actually monitor for other features on the Earth, such as looking for nuclear explosions, or part of the Tropical Rainfall Measuring Mission Lightning Imaging Sensor. This was a low Earth orbiting instrument, so instead of providing continuous coverage, it just gave you a snapshot of lightning activity. So the geostationary lightning mapper is our first opportunity to have an operationally usable lightning detector, as you can monitor lightning over a very large field of view continuously. Conceptually, the instrument is much like a large digital camera. Each little pixel on the GLM is looking at a particular part of the surface of the Earth. It's then trying to identify whether or not there is an optical brightness difference coming up from the cloud top compared to a background for each pixel. If you go back to the foundational course, that brightening pixel is the basic form of GLM observation called an event. We can then combine events into groups, kind of equivalent to return strokes, and eventually combine those groups into flashes. A few more additional details about the GLM itself. Looking at its field of view, it goes from about 54 south to 54 degrees north. So clearly that's going to cover pretty much every forecast office in the continental U.S., particularly once GOES-16 is up. We're looking at about an 8-kilometer resolution at nadir, kind of degrading out to about 14 kilometers at the edge of the field of view. So this is kind of one of those features that we want to talk about with some of our participants in the operational assessment. We have a couple of offices such as Duluth, Caribou, Bismarck. They're kind of on that more northern edge of the GLM. We want to kind of investigate how the GLM inspire our partners down in Miami or Houston. Sorry for that confusion there. Basically, the long story short, with those the northern offices, we're looking for the opportunity to work with them to kind of see how does the GLM work operationally at that kind of higher latitude, that higher parallax, compared to, say, the offices down in Miami and Houston. Again, as we mentioned, GLM observes intercloud and cloud-to-ground lightning, but it will not distinguish between the two. So again, this is where we can operate working with NLDN or Earth networks in conjunction. A couple of the design specifications, the GLM is supposed to have a 70% detection efficiency over 24 hours for the entire field of view with no more than 5% false alarm rate. Now, those values that I just gave there, those are designed as the specifications that GLM had to have upon launch. There's been a calibration and validation field campaign that has recently concluded, and they are working to really kind of nail down what those values are. So far from what we're hearing is the GLM is likely to exceed both of those design specifications. We'll know more later on this year as the CalVal team starts releasing their results. So I'll drop into the next thing here, really a quick distinguishing between the GLM, NLDN, and Earth networks. Kind of how do the various networks observe lightning compared to one another. So we'll have a little cartoon here. We'll look at a cloud-to-ground flash, an intercloud flash, and little white objects here are just little lightning sensors. And then we have the GLM up on GOES-R. One way to operate is in the very high frequency. This is how Earth networks, or the research lightning mapping arrays, kind of observe some of their lightning detections. This is kind of similar to the old analog television channels, so 83 gigahertz, those types of things. The advantage is it's very good location accuracy, and it's the best to observe intercloud lightning. However, it is very short-ranged, so we don't get a lot of range out of this type of detection. So for things like Earth networks where they have more range, they have to look at different ways to look at the lightning. So another way is low to very low frequency. So again, this is seen in Earth networks, the Viceless GLD 360, and the National Lightning Detection Network. This advantage is that you have good range and good accuracy with a well-placed sensor network. So as long as you don't have your sensors clustered in one little location or you have too far of a distance between your sensors, you can do a very good job at detecting particularly cloud-to-ground lightning observations, although you do have some capability to distinguish between ground versus intracloud flashes. Typically, though, your intracloud is going to be weaker than cloud-to-ground, and it's going to be more difficult to detect and may not always be detected. Another way, maybe something that you don't use in your local offices as much, is going to be very low frequency detection from Earth networks and the GLD-360, where this is used in very long-range observations. So we're talking looking out in the middle of the Atlantic or the Pacific Oceans. The difficulty with this is that it primarily only observes the strongest lightning flashes, which are mostly cloud-to-ground. The reason for this is it's dependent upon a signal kind of bouncing off the ionosphere, surface of the Earth, back to the ionosphere, much like a ham radio. And so this kind of signal has to travel many miles, thousands of miles at times, to be detected. It works best at night where you don't have as much solar radiation kind of influencing the environment. And then lastly, we have the geostationary lightning mapper. This is using near-infrared light. Currently, the GLM is the only operational instrument working with this. It does not distinguish between cloud-to-ground and intracloud flashes, but it can observe both. And again, this is where we want to use NLDN and Earth networks, kind of that distinguishing for you. There's going to be some attenuation and scattering by the clouds, and also it's going to work best at night, obviously, because you're not dealing with solar reflectance. But the nice thing is it has a very uniform detection efficiency over an area. The last thing I want to show is, for this particular section, is an image courtesy of the hazardous weather testbed. In the upper left is radar reflectivity over central Florida and part of South Florida. Lower left is showing the NLDN cloud-to-ground flash points and their associated density. The lower right is showing the Earth network's cloud-to-ground and intracloud flash points and density. And then lastly, in the upper right, this was kind of a correction done by the hazardous weather testbed, kind of correct the menu system and labeling system, with a corresponding color curve that we generated out there as well. What you're seeing is the spatial extent shown by the Earth network, not Earth networks, but the GLM event densities, as well as the X's are representing the GLM flash centroid points. And you can see that there is some good correlation with some of these large density pockets, Earth networks, GLM, NLDN, with the radar reflectivity. But you also see that the Earth networks compared to the GLM, you're getting much more spatial extent with the GLM data than either one of the other networks. So with that, I'd just kind of like to open up to discussion, comments, or questions about these kind of more technical details, and then we can drop into more of the operational components.
Yes, one question from Ms. Ryan. So what is the update cycle for the GLM data? How frequent are we getting it?
The GLM data are coming in at 20 seconds. Now that is the way that we're working with inside of AWIPS is that we don't want to show 20-second updates inside of AWIPS. That's going to be way too fast. It's literally going to look like it's flashing on the screen to you. So what you can do inside of AWIPS right now is that it's accumulating the data into 1-minute accumulations. So this is and then you also have other options inside of AWIPS to look at accumulations of, say, 5 minutes or 15 minutes. 15 is kind of getting beyond the scope of using it for severe weather applications, but that 1 to 5 minute accumulation gives you a chance to kind of see what's going on inside that storm that takes advantage of the rapid update of the GLM.
Is that the same as how the Earth networks and the NLDN accumulate, or is there differences?
They work in similar ways, yes. So NLDN, you have a couple of ways. You can look at NLDN as the accumulated density product. You can do the same thing with Earth networks. They're trying to match them up so that you have equivalent time intervals, so 1 minute, 5 minutes, those types of issues. Because you have point data for all three of these observation systems, you can also use the time sequence, so you can show all the points, how the points are color curved based upon if they're 1 minute, 2 minutes, 3 minutes, 5 minutes old. I don't think the GLM points are going to be quite as useful in that role as, say, the NLDN or Earth networks point data, simply because GLM has much lower spatial resolution than either one of those ground-based networks.
Okay, thanks.
Oh, you're welcome.
Also, what is the latency of GLM and AWIPS, as well as compared to NLDN and ENTLN?
I'd have to double-check the NLDN and Earth networks latencies. They have to, since they're updating every minute, they should be fairly rapid in what they're trying to do. I apologize, it's a vague answer at this point. The GLM itself, operationally, it has to be able to process all of its data within 20 seconds. But when you're looking at a 1 minute accumulation, you're going to be looking at some data that 1 minute makes up 3 files. So the earliest data is going to be maybe about 60 to 80 seconds old, whereas the latest data that makes up that 1 minute accumulation is going to be about 20 seconds old.
Okay, so pretty fast.
Yes. So pretty impressive that all the networks can do all this as quickly as they do.
Hey, this is Gail in Raleigh. Just to reference the hazardous weather testbed tests that were done on this data, I assume they were done on the 1 minute data and not the 20-second available data. Is that correct?
No, actually, it was using the 20-second data, but the AWIPS works to accumulate everything inside of it. Basically, kind of accumulates everything together internally in AWIPS.
Okay, I just wondered if there would be some differences in the assessment of lightning jump behavior with 20-second data versus the 1 minute data, if there would be a difference there.
I think that's going to be something that we'll be talking with the lightning jump folks as well to kind of see what's happening at that point, because I agree there could be something there. One of the things that we've seen in the past when looking at the lightning data, if you kind of break your time step up too small, it almost gets very difficult to see a trend develop because you're literally looking at it technically in real time at that point.
Right.
And yeah, exactly as you've discussed in the past here. So I think that's one of the things that we would like to look at as well, kind of from a research mode.
Okay, thank you.
Oh, you're welcome. Thank you for the question. Any other comments or questions?
Jeff, this is Dave. I have a question for you.
Absolutely.
I heard that one of the problems with the GLM getting into AWIPS has to do with a lat-long correction. I'm assuming it's a parallax issue. In the example that you have on the screen here, is that corrected or is that not corrected for parallax? Because there is a bit of a difference between where the max or the bullseyes are with the GLM looking a little bit further north and east of the other systems.
And again, Dave, that's an excellent question at this point. The example that you are seeing right now, this is not corrected. So this is showing there is the geolocation error through here. What is happening at this point, it is actually not a parallax issue per se with what we're seeing at this point. This is actually kind of a processing problem in the code right now in terms of taking the raw GLM data, processing it, and then plotting it inside of AWIPS. So there is an error right now that is being corrected at this point. We are expecting hopefully by about mid-August to have some corrections to that and then further corrections to occur as we go forward as we transition from the beta data status into the provisional and operational status later this year. But you are absolutely correct that what we're looking at right now, this does not have this is not corrected, and there is going to be some offset to this. I think in some cases we've seen an offset in the non-corrected data of about 20 kilometers. So that's a pretty significant change and obviously something that we want to see corrected.
Thanks, Jeff.
Oh, you're welcome. Any additional questions? Okay, well, again, thank you for the comments and discussion right now. Please feel free to ask any further ones as we go forward. And what I want to do now is I want to drop into a couple of very short examples as we go forward here. I don't want these to be exhaustive, talking about the synoptic environment and lots of details about what's going on in the particular case. The idea that we're trying to do here is just kind of quickly show graphically and kind of conceptually how you might be able to use lightning data in various ways. The first one I want to look at is a lightning jump in a severe weather environment. I'll say in this particular case that was provided to us by some forecasters, we kind of worked with some demonstration data to kind of repurpose this case for a GLM demonstration. We're looking at an environment that a moderate risk had been issued. The environment was favorable for severe weather, so just kind of keep that in mind as we walk forward through this particular case. What you are looking at here is in the upper left, we are looking at the pseudo-GLM demonstration data. Lower left is the National Lightning Detection Network observations, with the corresponding radar reflectivity in the upper right and the radar velocity in the lower right. So as we look at this, we see at this particular time step at 0310 UTC, there are no NLDN cloud-to-ground observations available at this moment. we do see on the radar reflectivity there are several strong storms, kind of in a loose line in this area, but as the forecaster told us at this point, none of these were analyzed to be severe at this stage. Additionally, we do see that since there are no cloud-to-ground observations in the NLDN, the demonstration GLM data is showing simply intracloud flashes. We see the spatial extent, we see how the lightning is kind of covering multiple locations, but we see that the density, the number of flashes per grid box, is no more than about 6, covering a 2-minute accumulation. So this is clearly a sub-severe situation right now. Really, if you're looking for severe weather, you're looking for 40, 50, 60 flashes as kind of a back-of-the-envelope rule of thumb. Not obviously the official lightning jump rules, but just kind of a back-of-the-envelope type rule of thumb. So let's kind of look forward through here. We'll jump ahead about 26 minutes, and we can see a couple of things are changing at this point. First, we see there are a handful of cloud-to-ground lightning observations in 2 clusters, one to the southwest with 3 negative and 1 positive cloud-to-ground flash, and a little further to the northeast, 3 negative cloud-to-ground flashes. At the same time, we do see with the radar reflectivity, the line is still fairly strong. It's filling in a little bit, and the storms are still looking fairly intense. There has not been a whole lot of change in the half hour or so from the previous image. However, the biggest change that stands out in this particular case is looking at the notable increase of total lightning observations from the demonstration GLM data in the southwest. Another way we can kind of visualize this, in addition to this kind of bullseye structure that we're seeing, is that we can look at the AWIP's tracking meteogram tool. Now, granted, this is a manual tool, so you're not going to be able to use it for every single case, but it gives you a quick way to show a kind of a time series trend of what is happening. So in this particular case, we have a favorable environment. We see that there are several strong storms being analyzed. So the radar reflectivity looks fairly similar between all storms, but we see that the total lightning from the GLM demonstration is emphasizing the southwestern storm. We look at a time series trend, we see a nice rapid increase. So the question comes down to, what would you do at this point? With all else being equal, would you consider issue a warning at this stage? So we'll kind of keep looking at this. We'll move forward to 0352 UTC. So again, like I said, going very rapidly through this case, more as a conceptual example than necessarily trying to walk through all the nuts and bolts details. We see again, there are a few more cloud-to-ground flashes observed by the NLDN, not really a discernible trend, a fairly flat trend in the cloud-to-ground lightning observations. We see that the radar, not really much of an update to it. The storms look fairly similar to what we saw even 30 minutes prior to this. The coverage is a little bit more, but again, not too much is changed at this point. A little bit more of some leading convection as well. However, again, looking at that southwestern storm cell, we have a very strong bullseye structure developing in that storm. That's indicating physically we have a strong voluminous updraft getting into the mixed phase region. Because we're into that mixed phase region, we have more charging, we're going to see more lightning, and that gives us a proxy observation of how that storm updraft is evolving, and that's likely intensifying. Also, we do see to the northeast, we see kind of a secondary cell that might be developing as well. If we look at the tracking meteogram tool again, we can probably say that more than likely, in a subjective sense, we have a lightning jump underway, as we've gone from very few flashes all the way up now to about 46 flashes in a 2-minute time period. This indicates when we see a lightning jump that's saying severe weather is likely. I'm going to tell you the type of severe weather, wind, hail, or tornado. That's going to rely upon the expertise and the knowledge of the local forecaster. As we kind of reveal the entire time series of this storm, we do see that there was a rapid increase up to about 50 or so flashes, and we did finally have a severe weather report at 0410 UTC in Jasper, Tennessee. This trend that you see, a rapid increase and then a rapid drop-off, that's a kind of a typical severe weather signature. You see the rapid increase as the storm core intensifies. Then a lot of our severe weather events, there is some sort of descending storm core during severe weather. Again, not always, but that's kind of something to kind of keep in mind. And when you have that descending storm core, you start cutting off your updraft, you start cutting off your charging mechanisms, and so your lightning degrades. Then finally, after the severe weather, we see that the lightning kind of starts dissipating as the storm dissipates itself. So as I said, a very rapid example, just like to, again, open up to any additional conversation or discussion that you may have about the concept of the lightning jump, kind of using it to kind of possibly, if you're looking at multiple storms in an area, you can use the total lightning data to kind of help identify which storm do I need to spend more of my time on. Again, in the warning environment, time is a very precious commodity, and anything you kind of do to kind of help decide which storm do you need to spend your time on can be a very useful tool. Okay, without any questions on this one, I'll drop to the next example. The following example, this is more of a lightning safety example versus a severe weather example. In this case, what we want to talk about are what are some of the advantages of total lightning from a safety perspective. As we've mentioned, the majority of lightning is generally going to be intra-cloud. So these are observations that Earth networks will see some of. The NLDN data can observe intra-cloud flashes, but currently the NOAA purchase of the NLDN does not purchase the intra-cloud components. You're not seeing intra-cloud lightning data with the NLDN. We also know that, in general, intra-cloud flashes will typically precede the first cloud-to-ground flash. And look at this chart through here. This is storms in the southeastern United States. Generally, there is about a 5-minute lead time between the first intra-cloud flash to the first cloud-to-ground flash. There's been similar work done by Dr. Don McGorman at the University of Oklahoma. He looked at storms in the central and high plains. He found a very similar trend with the lead time of intra-cloud to cloud-to-ground lightning, but also noted in more low precipitation style storms that lead time could be much larger, on the order of maybe an hour or so. And that kind of generally indicates how your cloud-to-ground lightning, you generally have to have some sort of precipitation process going on, reaching the surface to kind of help that lightning charge get to the surface and initiate a cloud-to-ground strike. Generally, the atmosphere is really kind of a good insulator and generally does not like to conduct electricity. So you really need to kind of build up a strong charge to be able to get any sort of lightning. In addition to this lead time, we have a brand new feature that's not available to the Earth Networks data or the NLDN data, and that's looking at the spatial extent of lightning activity. And we're going to illustrate that point in this example going forward. So to kind of look at this example through here, we're starting at 2158 UTC. A couple of things that we want to kind of look at. First, kind of let's set the scenario real fast. Imagine you're providing decision support for some sort of outdoor event. This can be any sort of event. It could be a sporting event. You could be working with your local airport for an airport weather warning, or it could be something more spontaneous. Unfortunately, it may be a fire where you have incident support meteorologists on, or an accident on the highway where you have individuals and first responders out there trying to work with the accident, and you're looking for safety for those individuals as well. So typically in this case, generally from a safety perspective, kind of a standard setup is a 5 and 10 mile range ring around your point of interest. You're just kind of looking to see where is lightning in relation to that point of interest. At this point, there's currently no lightning data being observed throughout the area, whether in the NLDN or in the GLM demonstration data. At the same time, too, we can look at our radar reflectivity. I have both the composite reflectivity in the upper right and the half-degree radar reflectivity tilt in the lower right. Looking at this, we have kind of 4 clusters of storms that we're paying attention to. 2 of them are kind of within our area of interest. One of them is off to the northwest. We have another one that's off to the southwest, moving directly towards our point of interest. So we kind of want to monitor what's going to happen with each one of these cells and clusters of storms. So let's move ahead just 2 minutes to 2200 UTC. And what we see at this point is we've had no update to the radar just yet. Now, again, this is a slightly older example, and so this was unable to take advantage of the sales algorithm that you now have available in the offices. So typically your radar updates are going to be a little bit better in conjunction with the GLM updates compared to this example. But looking at this case, we see no major updates with the radar at the moment, but we do see our first demonstration GLM data flash. There's no corresponding cloud-to-ground lightning activity with this, so we know this is completely intra-cloud. And in fact, this is an intra-cloud flash that's covering about 24 kilometers or so, as this is covering about 3 grid boxes east to west and another 2 grid boxes north-south. So a pretty good-sized flash already to look at here. So the question that we have to start asking ourselves is, we have a radar signature that's very similar across all storms. However, the pseudo-GLM demonstration product is showing that the southwestern storm is the electrified storm. We have to kind of start deciding what is this decision-making process that you're going to initiate at this point. So you have to start thinking about, do I have to worry about just the southwestern storm, or because the radar signature looks very similar across all of these storms, is it possible that all these clusters of storms could become electrically active at any moment? So it's kind of the thinking that you go forward here to decide what you have to do in this kind of decision-making process. So what I'll do now, I'll move ahead about another 6 minutes, and what we see at this stage, we see that southwestern storm, the reflectivity is still kind of increasing, both in the composite and the half-degree radar tilt. So it seems to be a little bit more the strongest storm in that kind of area, but again, we do see similar structure in all the other clusters. Our storm motion is still bringing this storm towards our point of interest, and we do see that the demonstration GLM is showing more lightning occurring. Now again, this is not necessarily a severe weather case. The maximum value through here is about 2 to 3 flashes at this point. So definitely not severe weather, but certainly a lightning safety component. We also see that at 2205 UTC, the first 2 cloud-to-ground flashes were observed. So again, the point that I'm trying to make here is the spatial extent is comparing what you're seeing with the point observations versus the overall spatial extent that we're seeing the demonstration GLM data. So in addition to that spatial extent, we did see that the intracloud lightning preceded the first cloud-to-ground flash by 5 minutes. So again, the question that I kind of bring up to you as you're thinking about this is, what decisions would you make at this particular point going forward? Now, I'll advance again about another 10 minutes, and we'll look to see what's happening, what's changing in this environment. The first thing that we see is we now have the first demonstration GLM flashes within 10 miles of our point of interest. We also see that some of the other storms are initiating lightning as well, and much like that first storm, this one to the southwest, we see lightning originating in the core of the storms, but also kind of advecting eastward, following kind of that kind of the upper level winds as charges being locked in the updraft and then being pushed downwind. We also see that our cloud-to-ground flashes remain outside that 10-mile range ring. So if we were just looking at the cloud-to-ground lightning data alone, we would say, okay, we still have time. The lightning data is not within 10 miles of our point of interest. However, what we're seeing with the GLM, with that spatial extent, we see that the intracloud lightning is already above or approaching that point of interest. As we showed in the animation earlier on, showing that example of a single lightning flash, we showed that cloud-to-ground lightning can come to ground from a lightning flash many, many miles away from the origination point of a lightning flash. At the same time, too, in addition to a lightning flash potentially being able to come to ground, a flash that's going overhead may actually induce charge at the surface. You can actually get streamers coming up from the surface, or you may even initiate a ground-to-cloud flash, which is obviously just as dangerous as a flash coming to ground. And we see that this trend continues at 2230 UTC. We now have our first flash, which is kind of edging its way into the 5-mile range ring at this point, once again indicating that the threat of a cloud-to-ground flash is imminent. We're looking at the cloud-to-ground data, still outside of 10 miles. And then lastly, kind of looking at the spatial extent, we move into 2232 UTC, and we finally have our first cloud-to-ground flash within 10 miles of our point of interest. So kind of summarizing this particular case, we had a lead time of 32 minutes from the first cloud-to-ground flash inside of 10 miles of our point of interest using the demonstration GLM data. This is about 5 minutes more than what we had available with the National Lightning Detection Network alone. So you might say in this case, well, hey, that's not too bad. 27 minutes versus 32 minutes, we're doing pretty good on both counts. What I'd like to do is kind of reverse the question and say, in this case, we were looking at a storm that was moving into our point of interest. What if this particular storm had initiated directly over our point of interest? Suddenly you change that question and you go from having a 5-minute lead time because of the GLM intracloud observations to a 0-minute lead time using the cloud-to-ground only data. So again, the advantage is we generally get a lead time with that intracloud observation, plus we have the spatial extent. So I'd like to stop here again and just kind of open up to any comments or questions that you may have about this particular case or any other questions you may have about the GLM at this stage. Okay. One thing I'll bring up too as well, and one of the things that we're looking at for the assessment is many of your offices are familiar working with NLDN, working with Earth Networks data, and these kind of interactions are what we're kind of interested to hear what you see when you look at the GLM data as well. You're familiar working with the GLM, not the GLM, but the Earth Networks data. We'll be kind of curious to see kind of how does the GLM compare to your kind of perceptions and implemented procedures that you're already working with Earth Networks or the NLDN going forward. So that's kind of one of the things that we'll be looking at in the future here in the assessment. The final operational case I want to show here, this again came from the Sioux Prep course, and actually got a lot of good reviews from the Sioux when they were kind of commenting about what we demonstrated. The reason for that is this is a null case. This is an example where the GLM data would not provide you good information for a severe weather case. And the feedback I received was that this added a lot of added much more realism to working with the GLM data. I believe personally, again, as the satellite liaison and working with the GLM, these data are going to be very, very effective for numerous things: lightning safety, monitoring storm convection, even severe weather operations. But we want to understand and know what are the cases where that may not happen. Where may GLM not be the most useful? This is a type of case where this would occur. So I'm kind of interested to show you what's happening at this point. So I'll go very quickly through this. The main point of interest is we are looking at this particular storm in the southwestern part of the image. We see on the demonstration GLM side, there are no demonstration GLM observations at all in this particular storm. And in fact, if you go back in the past 20 minutes, there had only been a handful of flashes in any event. The same could be said looking at the NLDN data. If you were to kind of follow what we've been talking about previously, looking at the GLM for lightning safety, plus for severe weather applications, we see this storm off to the northeast has kind of a developing bullseye structure. That's kind of indicating, hey, we have an updraft developing at this point. This is getting the mixed phase region. We're seeing lightning generation. I should probably put more of my attention on this particular storm because I have lightning here, and definitely it's a lot of lightning that's developing at this point. And in fact, that would be a correct assumption. Yes, that storm was intensifying, and this storm would actually produce an EF1 tornado later on. However, that storm that we were showing that had no lightning associated with it, it actually created or generated an EF2 tornado that actually hit downtown Huntsville, Alabama. So the question comes down to, what happened? The good news is, what happened is, we're talking about the physics of what's generating total lightning, what's generating the lightning in a given thunderstorm. This is not something where the GLM failed because some weird thing about the instrument or it's not going to observe lightning in a certain way. It all comes down to the physics of the situation and what's actually happening inside that thunderstorm. So what happened was, if we look at a cross-section of that particular tornadic thunderstorm that hit Huntsville, this is an extremely low-topped thunderstorm. It's barely exceeding 25,000 feet. At the same time, too, looking at the mixed phase region, minus 10, particularly above minus 20 degrees Celsius isotherm, there's very little of that storm into the mixed phase region. So it's a weak, not very strong updraft there. At the same time, that main storm core is less than 12,000 feet into the atmosphere. So it's a very shallow convection storm. So it's not really able to get into that mixed phase region to help generate charging and electrification. Another way to look at this, we can look due to sounding observations. We know that the minus 10 and minus 20 degrees Celsius isotherms were at 15 and 20,000 feet respectively. Again, looking at the radar reflectivity at those plane views at those isotherm levels, again, we're not seeing a whole lot. Maybe a couple of pixels, about 45 to 50 dBz tops. And again, that's not really very exciting of looking at an updraft in that mixed phase region. If you go back to the physical reasoning slide that we did at the very beginning of this presentation, you saw a nice big bright red spot of the radar reflectivity indicating a very strong updraft. We do not see that here. We also show that the freezing level, again observed by the sounding on that day, your main storm core is not even really getting that far above the freezing level. So the analysis is showing this was very shallow convection with the main updraft pretty much staying below the mixed phase region. With that reduced vertical extent, we're not getting into a region where you have ice crystals, supercooled water droplets, grapple. You're not getting the inductive and non-inductive charging developing at this point because we're simply not seeing a whole lot of different states of water in that particular storm cloud. So without that, we have limited charging, we're not getting a whole lot of charging, and so we're going to be limited in the amount of lightning production that we see. So this gives us several ramifications. I think first and foremost, this is demonstrating that we need to rely on forecaster expertise and experience to understand the environment that they're working in. That is going to be critical no matter what. I mean, in any sort of operational environment, kind of situational awareness is important. We understand that typically in the environments of low lightning production, this generally occurs in a high shear, low cape environment. Here we can get severe weather, but not necessarily severe weather that's going to generate a lot of lightning. We see this in low-top convection, but we can also see this with bookend tornadoes in quasi-linear convective systems. Again, that's kind of more of a dynamic situation. You have a boica going out. You kind of develop those vortices on the ends. That's not really going to generate any vertical lift to create lightning in this particular case. So what happens then is, A forecaster, if you can identify an environment at the times where you're in this high shear, low cape environment, you'll understand, hey, the GLM is likely not going to give me as much of a tool to observe thunderstorms on this particular day as they would in a more convectively active environment, high cape environment. If I do see any sort of lightning on this particular day, that's telling me something is really happening here because that storm is still managing to get to the mixed phase region. Otherwise, GLM may not be as useful in this particular case as it may be otherwise. So that kind of wraps up the null case. Again, I'd like to just stop and pause for a few moments to give you a chance to ask any questions that you may have. Okay, without any questions here, the final part that I want to do at this point is kind of do a quick summary here. What are the key takeaway points and the benefits of the geostationary lightning mapper? Main takeaway points are we're observing intercloud and cloud-to-ground lightning over most of the hemisphere. So we're observing total lightning. And being able to get that intercloud component, that's very important to be able to see what's going on inside that thunderstorm. So with total lightning, we can observe kind of the strength of the updraft, monitor how is the storm evolving. At the same time, too, GLM gives us the opportunity to look at the spatial extent of lightning. This is a new feature and a new capability. How far is lightning extending away from the storm core? We can use that for safety. We can use that for other features. Aviation, do they want to kind of fly into the stratiform region if we're still seeing a lot of lightning back through there? So uses for this, we can monitor severe weather, even in cases where your radar may be out, or data-sparse regions such as offshore, or other features are unavailable, other observation systems are not available, GLM details of what that storm is doing. Aid in lightning safety, and also from our aviation partners at the Center Weather Service Unit, Aviation Weather Center, they can monitor convection in data-sparse regions, oceanic regions, and just kind of see how are storms evolving. Are they persisting? Are they weakening? Do they have to make adjustments to flight routes and arrivals and departures for airports? At the same time, too, there's a lot of new research to come. Tropical cyclone intensity. Again, GLM works with optical observations of lightning. So how strong is that optical power coming back to the instrument? Can we use that for determining how strong is the lightning? Does that have a link to severe weather? Applications with fire starts. There's much, much more. So there's going to be a lot of research coming in the years to come going forward. So with that, I kind of want to wrap up here with a couple of details showing some GLM and also kind of providing some links and everything going forward to wrap up the presentation. So to wrap up this, these are showing some real GLM examples. I want you to kind of recall looking at this radar map. This is a really nice map I like showing from NOAA, showing the NEXRAD radar coverage across the continental United States. You can see, particularly out west, there's a lot of issues in radar coverage. We're better off further off on the East Coast. But again, if you have offshore interests, offshore marine zones, or you may have a radar outage, you're not going to get as much coverage. And so the GLM can kind of help fill in the gap there to understand what's happening. And in some ways, particularly out west, you can use this as a way to identify, hey, am I seeing any convection? Because do I see lightning? And that can tell me if I'm having precipitation, that might be a flooding event. Also, we can observe systems coming on shore. So kind of a first example, this is one I was showing more from our aviation partners. We're looking at the Advanced Baseline Imager 11.2 micron infrared imagery. So we're seeing a nice area of cold cloud tops extending over the Gulf of Mexico, very large region of cold cloud tops, and this is overlaid with the 1 minute, 8 kilometer GLM group density. So the groups are kind of that middle product for the GLM. The basic product are any kind of pixel lit up by lightning, that's an event. Cluster those in time and space, you get a group, kind of similar to the return strokes of a lightning flash, and then groups can be clustered into flashes. And just kind of looking at this simple still image, we can see a couple of things. First, we can see the structure of potentially a squall line or kind of this line of storms out over the Gulf of Mexico, where the lightning data almost serves as kind of a pseudo radar, if you will, kind of showing exactly where the main storm cores are located. And you can also see where more intense clusters are within that, underneath the cold cloud tops. At the same time, too, if you're an aviation forecaster, you can see gaps in the storm coverage. Again, I may not be the one who wants to fly in that particular plane, but you can see where the gaps are going through, where you can get through the storms. And then lastly, we do see where we can get very large flashes extending behind the main cluster of storms out to that stratiform precipitation. Kind of following on this particular example, we're now moving up north to Minnesota and Wisconsin. We're looking at a case here, kind of two examples. We're looking at the GLM, kind of these, I chose a color curve that was just using yellow here. Really the emphasis was not looking at the intensity, but just kind of the spatial extent of the GLM observations. Again, we're looking at GLM groups, 8 kilometers, 1 minute accumulation, and this is overlaid over the advanced baseline imager daytime convection red, green, blue composite product. The main thing to keep in mind with this product here, don't want to bog us down too much, the brighter yellows in the ABI here, that's indicating newer, more active convection. The reds are kind of indicating more mature, less vigorous convection. But as we see here in this 1 minute accumulation, we do see lightning over Duluth, Minnesota, kind of over central Wisconsin, and even down to kind of the Indiana-Michigan border. We go ahead 1 minute later, and we see that, again, not too much has changed over Wisconsin or Indiana, but now we see this very large flash extending practically from Duluth, Minnesota, up north past International Falls, Minnesota. This distance extended over 100 miles. So again, demonstrating just how far a lightning flash can extend from the main convective region. We look at an inset of the radar mosaic. We see the main convective line starting around Duluth, extending northward, and then the lightning flash extended kind of to the northwest into that stratiform precipitation. I'll kind of switch over here and show a 60-minute loop of that same event. And each frame that you see here is a 1 minute frame. What's interesting from this particular example is we're not just looking at a single long flash that occurred. We see that this long flash occurred multiple times throughout this 1 hour time period. So again, it's a very strong safety feature that we have to look at. And one of the reasons why we talk to individuals when we say the lightning roars go indoors, because many times the majority of people who are struck by lightning, they're generally being struck at the beginning of a storm or the end of a storm. Main reason for that, unfortunately, is people don't like to get wet. Once the rain passes on, people start going back outside, going back about their business, even though the threat of a lightning flash can still persist for a significant period of time after the rain has already passed. One kind of final real-world example, this is going out to the southwest. We're looking at a case where, again, weak radar coverage. We do see that the GLM is kind of highlights well where we do have good radar coverage. We see that main line of storms. Also gives you an idea of where is the main convection underneath the cold cloud tops on the ABI. But the real interesting thing here is up towards the Four Corners area, there's very little radar coverage at this point. It's very difficult. It's very high coverage at this stage. And we do see kind of a very weak observation by the advanced baseline imager. And corresponding to that, we see a singular GLM kind of group observation being seen at this particular point. So it's a very low flash rate. Not a whole lot's going on here. But that can identify, hey, something is happening at this point where we're not seeing it in radar. It identifies where we're seeing some convection. We might be seeing stronger precipitation occurring at that point than we might otherwise assume being able to look at the radar currently. So with that pretty much wraps up the presentation here. I did want to show a couple of slides here real fast. There are a couple of external resources that are available to forecasters, both participating in the assessment and for anyone who's just interested in the GLM. One of those is myself. I'm serving as the GOES-16 Geostationary Lightning Mapper Liaison, so please feel free to contact me with any questions. Also, the NASA Sport Lightning Training and Applications Library page is coming online, and we have a lot more material that we're working on to bring up there. So this has short little applications, examples that we've been showing with the GLM, and with the preceding lightning mapping arrays to kind of show us demonstrators for the GLM. And I'm also going to include the examples that we showed here today, but kind of break them up into short little pieces. We'll work also with Dave Riddell here to get the recording from this whole presentation available both on our webpage or our Eastern Region page as well. There's also the GOES-R webpage, always very good things to see there about the GOES-R instrument and the Geostationary Lightning Mapper. And, of course, also your own National Weather Service Lightning Safety page. I want to make sure I get that out there. A lot of the work that we've been talking about, showing some journal references. I'll talk about the Geostationary Lightning Mapper in that first reference. Looking at some of the lightning jump algorithm details for severe weather, and also kind of looking at a case of looking at some demonstration GLM data, looking at the May 20th tornado in Moore, Oklahoma, looking at demonstration data, how that might kind of integrate with current operations. And that's just a snapshot of journal articles, but please feel free to kind of look at the references in there, and they provide more information as well. And with that, I'll kind of end it here with a quick animation. Lockheed Martin released this a couple of months ago showing About 2.5 days worth of data on kind of a fancy display through here. I put this together as the corresponding AWIPS display showing the Advanced Baseline Imager and GLM groups through here. So I'd like to thank you all for your time and participation today.